we go ahead with our LoRa project. Today we will talk about the hardware build of our sensor entities. Let me recap just briefly where we stand with our LoRa weather station. Originally, I just wanted to investigate the coding and the capabilities of LoRa boards. However, along that way, I found so many interesting details that I want to share with you. I also want to share methods, construction, application ideas, and tools with you. This is why there is still a number of videos to come. You could already see the level of details in the past episodes when solar powering, batteries, concept and cases were touched. The recorded experience that was presented in the former episodes and the given spreadsheet tools shall be an extra value for you. It helps you to dimension your own projects. In this episode we will talk about the schematics, the sensors and the LoRa board's hardware. Our hardware concept foresees 3 weather sensors. There is the sensor number 1, together in the case with our little server. It is an easy one because there is no wireless technology involved. But it is a bit tricky anyway. We will talk about it in a later episode when we talk about the server entity. The sensors number 2 and number 3 shall be mobile or at least movable. We want an indoor sensor entity which can be powered by any USB charger. It shall have an external antenna with SMA connectors so that we can experiment with different antennas. Furthermore, we want a completely waterproof outdoor sensor that can run autonomously with a solar panel. Using the set outdoor sensor, we have seen already a number of solar power experiments and insights in earlier episodes. I think you guessed it now. All entities shall be capable to run on battery so that we can move them without losing any information during operation. Of course, we want automatic restart capability during charge up in case the battery was empty. And we do not want to push a reset button in case we want to update the software, because we don't want to open the case again and again. Our little sensor entity is dedicated to transmit temperature, humidity, air pressure and battery voltage to our little server via LoRa. We know that our little server will update its presented values every 5 minutes. Since we do not have a handshake protocol between the LoRa transmitter and receiver, we need to send the data slightly more frequently than the 5 minutes. We decided to send a data package every 3 minutes that contains all the data. This makes sure that each time the server updates its presented values, there will be always an updated value available. For the radio frequency, we chose 866 MHz, which is within the regulated band for LoRa in Germany. I chose this frequency instead of the usual 868 MHz because this frequency is used for LoRaWAN applications from the Internet of Things networks. And I don't want to interfere with these networks. In case you need to operate in other frequency bands that are defined in your country, please make sure to order the right LoRa boards. You will find the supported frequency bands in the supplier specifications of the boards. The defined frequency bands for your country you will find on the internet pages published by the local regulatory body. There is LoRa board versions available for 433, 868 and 915 MHz. The filter networks on the boards and suitable antennas, of course, are different for the different frequency bands. This is why it is so important to choose the right ones. If we want to power with batteries, it goes without saying that the complete hardware of the sensor entity needs to run on low power. Usually this can be only achieved when the complete hardware supports sleep mode. We try to apply this as far as possible. Next, we look at the schematics of our outdoor sensor unit. For the case being absolutely waterproof, first we choose a simple helical LoRa antenna isolated by a heat shrink. It can be used inside our sealed plastic case. And second, for the power connectors, we use banana sockets that we sealed with glue. Inside the case, we find the charge controller that uses a TP4056 chip to charge our lithium-ion battery. A voltage divider realized with two 500 kΩ resistors is used to create a suitable input voltage for the analog inputs of our ESP32 board. We use pin number 39 for this purpose. The battery is connected via the standard battery connector on the board. The sensor is connected with 4 wires. We have voltage in and ground that we connect to the corresponding pins on the ESP board. Then we have the data connections of our I2C bus. The serial clock is connected to pin number 13 and the serial data is connected to pin 21. The indoor sensor unit is similar to the outdoor unit. However, it just comprises the sensor, the TTGO board, the battery and the voltage divider. Our TTGO board has an integrated charge controller so that the battery can be charged via the USB cable. For this purpose I used an old USB charging cable. I own several from a number of USB gadgets. And by the way, this is a tip I want to give to you. Don't dispose electronics cables. The stuff can be still valuable for tinkering. In my case here, the USB cable remains constantly connected to the board. And then there is another hint that I need to give you on USB cables. Most of the simple USB charging cables cannot transmit data. So, in case you want to use your constantly connected USB cable to download improved code, or you want to use the serial interface of your ESP board, please make sure that you use a proper data cable. Now back to the schematics. The switch that I mounted to the indoor unit is used to separate the battery in case I do not use the entity for a long time, because the voltage divider would discharge it over several months. The SMA antenna connector allows on one hand to change the antennas, and on the other hand we can measure the actual LoRa transmit power on that connection. Here's now some hardware pictures together with some additional tricks and tips. While I'm happy with the banana sockets that I bought, I'm not with the banana plugs. And yes, they were cheap, but I was really disappointed because they didn't make a proper electrical connection. What? Yes, plugs that doesn't conduct properly. In case you have the same problem with cheap banana plugs, here is the clue. Simply solder the head of the plug to the contact springs. I indicated this with the yellow arrows on the picture. In my case, they work perfect now. On the lower left side, we have the TP4056 charge controller. It is really a nice device that allows charging through either USB micro connector or directly through the board's input pins, which I used. Furthermore, there is a tiny red LED indicating charging and a tiny blue LED indicating that your battery is fully charged. And you get it all for a reasonable price. Nice, isn't it? The picture in the middle shows the indoor sensor entity while charging with an old USB charger. The antenna used is a commercial rubber-coated helical antenna that was delivered together with the TTGO LoRa board. The antennas you can see in the background here are self-made from an SMA plug, copper wire and heat shrinks. I will show in a later episode how to make them. On the right side we have a close-up from the sensor and how it is attached to the case. In order to protect the sensor, I glued the plastic part from a tape roll to the case here. When the entities are running only on battery, I made the experience that they run about 10 to 12 days with one full charge. This could be significantly improved by low power boards. In case you are interested, please go back to the earlier episodes where we talk about the dimensioning of our solar generator and the battery. Here's now the outdoor sensor unit in action. The picture was taken during a thunderstorm with heavy rain. In the meantime, it works for more than 140 days autonomously on the balcony. We had sun and rain as well as hot and cold weather during this time. Obviously, the case remained waterproof. Very good. That was the intention. Since the sensor should measure air humidity, we mounted it outside the case. The through holes for the cable were sealed with glue. Then we covered the sensor board with a small housing that is glued to our waterproof case. It has small drill holes on the bottom to let the air flow through. I think it becomes clear that the little sensor board needs to operate in humid air. Therefore, I sealed the whole little board with transparent nail polish from my wife. For sure, any other water-resistant transparent varnish would also do the job here. But be cautious here. You really need to take care not to paint the tiny little holes of the little metallic box you find on the sensor board. This is where the actual sensor is sitting. I covered it with tape while painting the board in order to avoid this. Here comes the indoor sensors entity in more detail. During charging, we see the red LED light from the integrated charge controller. You can as well see the battery that is glued to the bottom of the case. The processor board doesn't need to be fixed. The voltage divider is directly soldered to the battery wires and coated with heat shrinks. This works fine, but anyway, here is a hint for improvement. Resistors used for the voltage divider typically have a tolerance of 5%. This means that with bad luck in choosing the resistors, your voltage measurement tolerances can be even worse. And furthermore, it will vary between every voltage divider you build. This means that even when you adjust your voltage measurements with a software factor, you still have a difference between the different entities. Of course, you could adjust this as well with different software factors, but then you get different software versions for your entities. Engineers don't like this, because this is more effort and the source of errors. Here is the improvement idea now. Put your voltage divider better on a little board together with a 100 kilo ohms potentiometer between the resistors. With the potentiometer you can compensate the resistors' tolerances, and you can conveniently adjust your voltage divider while measuring the battery voltage with a multimeter in parallel. With that simple measure, you can improve your voltage measurement accuracy, and the software remains the same for all entities. The summary. We defined the proper concept and the requirements for our hardware, which was derived from the overall concept that we defined in earlier episodes. The important hardware functions were discussed and a valid realization proposal was made. In addition, some experience as well as some tips and tricks for improvements were shared. Do you know what's better than learning from own mistakes? Well, the answer is learning from others' mistakes. I hope you enjoyed this episode and you might be able to do it right the first time. The coming episodes will cover the coding of our sensor entities. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.